didn't start the recording.
Okay, I've started it. So,
Okay.
um, this is stupid. Okay. So the reality is, yes, this is not a super important thing in the context of uh Siley, but this is the most important thing in the context of real world circuits. And so nodal analysis will be in division B. I mean, yes. Because like nodal analysis is a very general circuit analysis technique. So if you know nodal analysis, you can solve any circuit that you'll get thrown at you with division B, division C, college class, grad student, whatever. Nodal analysis is the most general circuit analysis solving technique. So, anyways, when we put a p-type material next to an n-type material, cool things happen. Okay. In particular, we form this region where there are no free charge carriers. What do we call that region? Depletion zone. Exactly. Oh, sorry, Chris. Um, so if I apply a high voltage to the p side, what happens to this depletion zone? There's some guesses happening. So yeah, Vian, go ahead and guess and explain why your guess is what it is.
So like basically if you add a battery to the positive side, it's gonna actually decrease in size. And then if you flip around the battery, so the positive voltage will go to the N-type side. That means the depletion zone is gonna increase in size.
So why does you're right, the depletion zone, oops, I don't show up, but the depletion zone does decrease in size when you attach the positive to the P side. But why is that? Can you give me a reason?
Yeah, so like uh for the positive P-type side, when you add the voltage to the P-type side, you're actually having the positive charges move away from the P-type side. And then in the other way around, you're having the electrons move away, which is actually increasing the size when they're going into the depletion zone.
Yeah. So I think oops, that was not a straight line. Okay. You're saying the right thing. So basically, the positive, you can think about it. This is not actually what happens really, but you can think about it like this. The positive charges are being pushed in and invade the depletion zone, okay? Because positive repels the positive, right? Positive charges flow away from high voltage. So that's how I remember that. But really, it's just terminology there. So now in this circuit, the basic circuit element of a diode is a PN junction, okay? So suppose the diode here is an ideal diode. If it's in forward bias, if current's flowing through it, it drops 0 volts. And if it's in reverse bias, no current flows through it. So in this circuit right here, how much voltage does this diode drop? Someone give it a guess. In this circuit, how much voltage does the diode drop? Maybe someone other than Beyond. Beyond's on our poll. Gotta ask someone else. Yes, Aiden's right. 0 volts. It's in a forward bias, right? So the current flow is in this direction in this circuit. That's in the direction that the diode wants current to flow. So actually, it's like this diode doesn't even exist, and we just have a wire, and this resistor drops to 6 volts. Okay, all the voltage dropped by that resistor. Okay, so now we have our preliminaries on PN junctions established. Let's, yeah, Atarf.
Oh, why would you even need the diode in the last circuit?
You wouldn't, right? But say maybe the 200 ohm resistor is like something that gets damaged if it has current flowing in the wrong direction. And say I'm dumb and I attach that battery in the wrong direction. Well, then I would accidentally be killing my resistor. I'd be breaking it. And this diode would make sure I don't do that. In practice, diodes are the biggest application of that is an LED, right? An LED is a type of diode, and it just emits light when current's flowing through it, and it blocks current in the other direction. So why was it 0 volts? It's 0 volts because it's an ideal diode and current is flowing through it. So it's in forward bias. Okay. In practice, it would drop just a little bit of voltage, right? But we model it as dropping 0 volts.
Yeah. Just to add on to that, it's a 0 volts because current's passing through it, and since it's in a forward position, it's not stopping any sort of voltage from going through. It effectively is just like a piece of wire when it's in forward voltage, and the current's going through it in the right direction.
Yep. Okay, so now let's quickly justify why talk about transistors. So a lot of people, myself included, say the transistor has been the most important technological development in all of history, more so than the wheel, more so than all of this. The transistor is the most important thing. It's a thing called Moore's Law. Maybe you guys have heard of it, maybe you guys haven't. But it says that the number of transistors on a single microprocessor chip doubles every 2 years, okay? So the first transistor came out from Bell Labs, I think in the 1950s, maybe 1960. I don't remember exactly. Well, I don't remember because I wasn't alive, but also I don't remember because I don't remember. But it was just Bell Labs is now AT&T basically, and it's just by as an empirical trend that people have found over time is that every 2 years the number of transistors on a given chip doubles to the point that now we have 100 billion transistors on a single chip on the Apple M2 Ultra, and it only continues to grow to the point that we're now approaching the point where transistors are so small that these effects like quantum tunneling through the gate and things that we'll talk about, we're not going to talk about that, but quantum tunneling and certain small things in the transistor are limiting us. We are approaching the limit of how small we can make these things. And that makes a lot of people scared for the semiconductor industry, actually. But my point is, transistors are what lead to technological development. The reason we don't have computers that take up whole rooms anymore and I can just hold my phone and do whatever I want on my phone is because I can fit so many tiny transistors inside this guy. Okay? So let's talk about what transistors do. Transistors can be super tiny, but they do so many different functions. In real-world circuit design, real-world electronics hinge around the transistor more so than any other circuit component. Okay? So let's get into it. We're going to talk about the MOSFET. MOSFET stands for, and it's a big chunk of letters, metal oxide semiconductor field effect transistor. Okay, I'm going to explain what all those words mean in a second, so just bear with me. So to construct a MOSFET, what we do is we start by making this slab of p-doped material, this big block of p-doped material. So there's lots of holes in there, okay? Then in the corners of that p-doped material, we put 2 bits of n-doped material, okay? So these n-doped materials have a bunch of negative charge carriers sitting around, okay? A bunch of negatives. And the p-doped has a bunch of pluses sitting around, okay? So just one more. Now we form these 2 depletion regions between these junctions, right? You see how there's p-n junctions here? It's the exact same thing as before. It's just now the p-n junction is inside of the p-doped material because we put an n-doped little hole into there, okay? Now, is there a way for us to connect these n-doped regions? I want to be able to have these electrons flow from there to there, because then maybe I can attach a wire into there and a wire into there and then have a circuit. And if electrons can flow between these regions, then maybe I can control that electron flow very carefully, okay? To do that, we put a layer of oxide and a layer of metal, okay? So this metal, we can now apply a voltage to, okay? We can put some voltage there. And the oxide makes it so that whatever voltage I put will not lead to any current. This is an insulator, okay? It's an insulator. So no current can flow through that oxide layer. However, when I apply a voltage to the metal, it still has an effect. It has a field effect. Okay, yeah, Naman?
So it is basic so oxide on metal would be like rubber wire on the like rubber on the wire of our computer charger.
Yeah, exactly right. It's the insulator. So really it's not an oxide that's around your computer charger, but it is an insulator. It's a different kind of insulator. And what it does is prevents current. So you're saying the right thing.
Is oxide liquid or?
No, oxide is just it's a solid material. It's a solid though.
Okay.
Yeah. It can depend on what it is. It could be different types of oxides. It's a chemical thing.
Okay.
Yeah, Chris?
So why are we even applying voltage to the metal?
Good question. So as we'll see shortly, that's the gate. And it basically allows us to control how much current flows. But we'll get to that. So you're asking the right question, but we'll get to that soon. So If we apply a positive voltage to the metal, the insulator blocks any current, okay? But it still has an effect. These drawings are garbage now. It still has an effect, okay? That voltage that we apply to the metal is still felt by the p-doped material, okay? And that positive voltage is going to push the positive charges to the bottom of the p-doped material. And it's going to leave behind some minus charges at the top, okay? Because remember, just because the p-doped material has a lot of positive holes sitting around doesn't mean it has no electrons. It has some electrons that are available and freely floating around. We call them the minority carrier, okay? In a p-doped material, holes are the majority carrier, electrons are the minority carrier. And so those electrons get attracted to the top there, okay? And if we apply enough voltage, we attract enough electrons that we form what is essentially an n-doped layer. This is called inversion, the inversion layer. And we've attracted enough minuses that this layer can you see my cursor? I think you can. This layer where my cursor is looks like an n-doped layer, okay? It becomes inverted. It's still in a p-doped material, but because all the minus charges have accumulated at the top there, it's inverted and become n-doped, right? This is greatly exaggerated. The reality is a super, super, super small, super thin, inverted n-doped layer, okay? If we apply even more gate voltage, we make that layer even larger, to the point that now we've connected the n-doped regions. And so now my minus charges sitting here can flow to my minus charges sitting here, okay? In other words, we've opened the gate, okay? And I'm using that word gate very carefully here. We've opened the gate for current to flow, okay? So let me just go through, Avatar done.
Can you is it possible to switch the p-doped material on the n-doped material?
Yes.
That's called a P. Very end of the lesson, yeah.
That's called a PMOS transistor. So this is the NMOS transistor. The opposite of this is the PMOS transistor. And when we combine them, you get a CMOS inverter, complementary MOS inverter. And that is the basis of all digital logic. That's what lets us do binary things. Not the diode, but really that's the thing. But we'll get to that. That's coming. So let me just go through what I just said again before we move on, okay? We start with a p-doped slab of material and we put these n-doped things in the corners, okay? What we want to do is connect the n-doped regions because the n-doped regions have lots of electrons. Electrons are the majority carriers in those regions, and we want to let those electrons flow, okay? So we put a layer of oxide, some insulator, so that current can't flow from above this material into the material, and then some metal on top of that. Then when we apply some voltage to the metal, there's no current that's going to flow because of that insulator, but the effect is still going to be felt by the p-doped material. And so the positive charges are going to be pushed away from the positive voltage, and the negative charges are going to come up to the top. There's not many negative charges because those are the minority carrier in the p-doped material. So it's a very, very small number of negative charges that as we apply more and more voltage up here, invert because they all accumulate to form what looks like an n-doped layer. And even though it's still p-doped, the negative charges have accumulated to make it look n-doped. So it's inversion of the layer. And as we apply even more positive voltage up there, we form a proper channel for these electrons to flow in, okay? So this is the metal oxide semiconductor field effect transistor. Do you see why it's called that now? We have metal, we have oxide, and we have semiconductors, and the field from this voltage affects to have a transistor, okay? That's why it has this really complicated name. Those are just the components of it. It's a metal, an oxide, a semiconductor, and it's a field effect transistor. There's other types of transistors that are also very important, like the bipolar junction transistor, but those are not, well, I say this cautiously, those are not field effect transistors, and they're also not as ubiquitous in modern circuit analysis. So we're really going to focus on the MOSFET. But if you're interested, the BJT is the other one that you want to look at. So are we all clear up to this point? Do we all understand what's going on? Why is chat disabled? Jay, Ed, can you fix that? I don't know why chat is disabled. Okay, I don't know what happened there. Vian, yeah, what's up? Sorry. Vian, you raised your hand.
Yeah, okay. So like in the other one, the last question, like why did we have to put the insulator?
Yeah. So if we didn't put the insulator, this is metal, and this is a semiconductor, which can act like a conductor. And so I'd have current just flowing from that metal into the semiconductor. And that means we no longer have current just flowing from this left corner to the right corner, but we have some more current flowing into it. And that kind of defeats the purpose that we're trying to go for here. We want something that can control the amount of current that flows, right? A resistor is just V equals IR. We want something that has a more sophisticated relationship than V equals IR. Like V equals IR, but maybe we can control the R. And that's what this does. This positive voltage is meant to control the R without introducing more current. Are the yellow and pink areas yellow and pink? A bad news, dog. You might be colorblind. Oh, do you mean the next slide? Yes. Okay. Sorry. Um, yes. Yeah, you can think about them like the depletion layer. Actually, for what we're talking about here, the depletion layer is like not so important. But yes, you're right. So if you put a bunch of voltage to the metal and oxide, so then it makes a channel. Yes, Albert, that's correct. Okay. So now these different parts have different names. Okay, let's just break it down bit by bit. This thing on the left is the source. That left corner we call the source for the transistor. Okay. What is a substrate? Good question. The substrate, if you've done any chemistry, you know that we talk about substrates as like where the reaction takes place. Okay. In the context of here, the substrate is this big block of p-doped material. The big guy that hosts everything is a substrate. You can think about it like just the house for all these other components. That's what a substrate is. Okay.
Naman, do you have a question?
What is the pink thing on the previous slide on the end of?
That's the depletion layer. I didn't really draw it accurately. It really looks more like this in practice, but that's the depletion layer. So yeah, the source we connect to the substrate. Think about why we do this. If we didn't do this, say the substrate, this bottom layer, was at a different voltage from here. That means I could like forward bias PN junction. Then I might have current going in this direction. That's no good. We don't want that, right? All we want is current going here to here. That's the only, or I guess in this context, here to here. We don't want any current anywhere else. So we need to make sure the source is at the same voltage as here. Okay. Now, how does oxide work? Oxide is just an insulator. Don't worry so much about like how it works. Just accept that it's like rubber around a wire. It's an insulator. So now electrons flow from the source. They flow from, let me use this color, the source to the drain. Now you'll notice this ID points in the other direction. Remember, current flow is in the opposite direction of electron flow. This is just the convention that we use in circuit analysis. Electrons flow, the electrons are negatively charged, and we talk about flow of positive charges. So the current flow is opposite to the direction of electron flow. So why does it flow from source to drain? That's a good question. It's because, well, I should say this. So first of all, we've tied the source to the substrate, and we've also forced this value VDS to be positive, okay? So since this voltage is higher here and lower here, current will go like in that direction and electrons flow in this direction. But actually that's a very insightful question because it's actually not obvious why ID can't go in the other direction. For now, I'll just say accept it at face value that the current can only go from drain to source, or in other words, electrons can only flow from source to drain, okay? But remember, when I'm saying electrons flow from source to drain, how do we form the channel? So it's what we talked about earlier. When we apply a voltage right here to what we call the gate, we attract up the negative charges and we form a little channel for those negative charges to flow in because we pulled them up by applying the positive voltage there. Okay. So the gate, like I just said, controls that channel. It controls the size of the channel. If I apply a really big gate voltage, I open a really big channel so I can have a lot of current. If I apply only a teeny bit of gate voltage, I don't open the channel much, and I only allow a little bit of current, or maybe no current at all if I don't apply enough gate voltage. Maybe my channel looks like this, and so the electrons have no way of reaching over there. So there's some threshold voltage for the gate, and I'm using that term carefully, threshold voltage, remember that, such that I can connect these regions just barely. And if I use a ton of gate voltage, then I connect these regions a lot. Lots of current can flow. Okay, so there are so many electrons that need to be transported. Yes, that's exactly. A channel is like a bridge allowing for electrons to be transported. Actually, the analogy I'll show in a second is like a faucet on a sink. There is a limit to how much current we can put. So that's called the saturation current. And if you think about it, this gate is actually really tiny. Like I said earlier, since electrons are the minority carrier in this p-type body, the gate is super, super tiny. Okay? And so there's only so much current that we can push through here. Okay? If I apply a super big voltage VDS, it's trying to push so much current through just a tiny tube. It's not going to explode. Nothing bad is going to happen. So the gate is tiny because remember, in the p-type, we have lots of pluses floating around, but only a few minuses. And what we've done is we've just pulled those minuses up to the top, but there's only a few minuses. So this channel is just tiny to begin with. It can't be large. So shouldn't the channel be thinner as you put more voltage? So I see the misunderstanding you're having here. Remember, the positive voltage that we're applying at the gate will pull the negative charges up, okay, and push the positive charges down, okay? Positive charges go away from positive voltage. Negative charges go towards positive voltage, okay? So this sounds a lot like resistance, right? The amount that something prevents or allows current, that's exactly what resistance does. And indeed, we're going to model transistors as variable resistors quite soon. Now, finally, we talk about all voltages relative to the source because the body is tied to the source, okay? So when we talk about VGS, this thing is just VG minus VS. And really, you can think about the source as just being ground, okay? So this basically is VG, but it's just relative to VS. VDS is just VD minus VS, okay? Why is VG minus VS? So since the body is also at VS, VS is basically our ground voltage for the transistor, okay? And so VGS is just the symbol that we use to say G minus S. VDS is just a symbol that we use to say D minus S, okay? What is the equal to? Are you talking about like this thing right here? Because that's just the symbol for a battery. We haven't shown that symbol, I guess, but that's another symbol that's commonly used for batteries. Basically like this. So the long part is the positive side, the small part is the negative side. Yeah. I don't see who raised their hand. Someone raised their hand.
Is there like a meaning if the battery has like more than one set of a long line and a short line?
No.
Like a short line? No? Okay.
No. If someone says there is, then they're just being dumb. Some people might argue that having more lines means it's a stronger battery, but they're wrong. Don't do that. That's terrible circuit drawing practice. I draw my battery just like this, right? So the short side is the negative side, the long side is the positive side. No extra lines, none of that. And if you want to draw an AC source, you draw it like this, and then you symbolize positive like this and negative like this. The wiggle means it's variable, but that's all it is. So there are some key parameters to the MOSFET. Now we're not going to do the math in the lecture. Maybe in an extra session we'll talk about it, but we're not going to do it here. But you do need to remember a few of the key parameters of the MOSFET because your understanding would not be complete without them. So when I apply the gate voltage, remember, the gate voltage starts by forming a channel, okay? As I apply more and more and more gate voltage, I start to let that channel become a little bit larger until finally the channel connects these two regions. But the gate voltage doesn't do that at like 0.01 volts. There's a certain threshold voltage that it needs to reach before the channel is actually formed. So we just call that the threshold voltage, and it's just a property of the materials and the geometry and the certain things that you are empirically determined. You really don't calculate them. You have to determine them just by testing your device. Okay, like in the lab. And even if the channel is formed, the voltage in the two end regions is the same, right? Like if there's no voltage difference here, the voltage here is the same as the voltage here. And so no current's going to flow, right? Two regions at the same voltage are not going to have current flow between them. So this parameter right here needs to be non-zero. VDS needs to be non-zero for current to flow. Okay. In particular, VDS needs to be greater than 0 because for reasons that I did not explain very well, current flows from drain to source for this guy. Okay. VDS. And now, if we increase VDS at a given gate voltage, the current will also increase. Okay. Just like a resistor. Remember for resistor, V equals IR. So R is set, and if I increase V, I also increase I. We get the same behavior here, but only to a point, okay? Eventually, for a given channel length, we're sending so much current through that channel that we can't fit any more current in there, okay? We call that saturation, and that's this part of the curve. We're trying to push so much current through them, but we reach the maximum. You can't fit any more current, okay? So there's 3 regions. There's cutoff, when the gate has not yet formed a channel, okay? So no current can flow. If the gate voltage is too low, we call it cutoff. If the gate voltage is large enough, but VDS is small, then we call that triode. And that's where the transistor kind of behaves like a resistor, okay? Changing the voltage, yes, we can fit as much current. We basically get what is like V equals IR, but it's a nonlinear relationship. It's more of a quadratic thing instead of linear, okay? And finally, saturation is when we're putting as much current as we can, but we just can't fit any more current. What does the drain do? So yeah, the drain and source are basically like symmetric things. But since we've tied the source to the main body of this transistor, the drain is going to be where the electrons go. So electrons come from the source and go and end up in the drain. That's why we call it that, right? But just remember, because we model current as the flow of positive charges, the current is the opposite direction. Why in the triode, oh my goodness. Why in the triode does the transistor act like it's a resistor? It's because the current varies with respect to voltage, right? That's the key property of a resistor. This is the equation for a resistor, Ohm's law. And what a resistor does is it gives us, when we change voltage, we change the current, okay? The only reason I'm saying triode is like a resistor is because when we change voltage, we change current. You can see clearly this is not a linear relationship. It's obviously nonlinear, but current changes when we change voltage. That's why it's similar to a resistor. When we get to saturation, current is no longer changing with respect to voltage, okay? So it's no longer like a resistor, it's at the maximum value. So now one thing I want to point out very clearly, is that a higher VGS leads to a higher saturation current. So these values are kind of cut off here, but so right here is 1, right here is 2, all the way up right here is 5, at the top is 6. For a higher value of VGS, we get a higher possible value of the current. So the y-axis here is the current. You can see for higher given values of VGS, we get a higher current. And that's because a bigger G means a bigger channel, which means we can fit more current until we reach the max, okay? So before I take any questions and just kind of make sure everyone's still on board, let's recap what we have so far with an analogy. The best way to think about a transistor is like a sink with a gate, okay? So if VGS, if the gate voltage is less than the threshold, what does this mean for our analogy? If the gate voltage is less than the threshold, what does it mean for our analogy here? Someone give me a guess. You apply a negative voltage to the gate. So yeah, if you apply a negative voltage to the gate, it's like you're below the threshold. There's depletion and enhancement mode NMOS transistors. We won't talk about those. But for our purposes, the threshold voltage is always positive. And so if the gate voltage is negative, you're not going to meet threshold voltage, and that's that. You're done. Game over. But what does this mean for our analogy? If the gate voltage is less than the threshold, what does that mean? Someone give me a guess. Current does not flow. Yeah. It's a vague question, but yeah, current does not flow. That's a correct answer. Basically, the gate is closed. We've just closed this gate off. So it doesn't matter how much voltage I'm trying to send through, it's just off. But if the gate is open, like on the right, because we've opened the gate voltage, now we can send through current based on VDS. There's a maximum value because there's only so much current that we can send through here at once, right? And if we open the gate more and more, if we apply a greater gate voltage, we can send through more current. But VDS is what controls that current, okay? And if VDS is low, it doesn't matter that the gate is open because no current's going to flow. So what the point is here is that VGS, the gate voltage, determines how much current can flow, but VDS determines how much current actually does flow. So VGS is the gate voltage. The S is basically saying it's relative to the source. So it's the gate voltage minus the source voltage. VDS is the drain voltage minus the source voltage. Unfortunately, there's no interactive activity today. I know our course kind of sucks with that. We haven't done much interactiveness. I apologize for that. That's just our bad. But yeah, VGS determines how much current can flow. The VDS determines how much current actually does flow. Are we all clear on that? Are there any questions at this point? Any confusions? Okay, let's move on then. So this is what I'm not going to describe this actually. I want to get to the CMOS stuff. But this is what the MOSFET looks like in a circuit, okay? It's a 3-terminal device, okay? So the gate, no current flows into the gate. That does not happen, okay? The gate just regulates how much current can flow through here, okay? In particular, there are 3 regions of operation. There's cutoff. Cutoff is when the gate voltage is too low, so there's no channel and there's no current. It's like that sink faucet is closed. You just blocked it off. Okay? Triode is when the gate voltage has opened the channel and the current depends on VDS. And saturation is when the voltage is so big and we're just filling that channel up. We can't fit any more current. So there's equations that describe this. And you can tell these equations are pretty nasty. Okay, so that's why we're not going to do any math with the transistors. It's just too nasty for us to work with. Not in Kansas anymore. This is no longer just as simple as V equals IR was for a resistor. And so to answer your question, how can VGS determine if a current can't flow? This is why. These equations are fundamentally dependent on VDS, but the condition is dependent on VGS, okay? So notice how the current is dependent on VDS, but the condition to use that current is dependent on VGS. Okay, so equation-wise, that's why. But even just like physically, remember, why does it have to be so nasty? It's a good question. The gate voltage is what opens the channel. It opens and closes the channel, but there's no current that flows through the gate, right? Because of that insulator layer, okay? If the MOSFET isn't cut off, there's exactly 0 current. It's a good question. It's a very good question. I'm going to say that there's a leakage current, but it's not necessarily a leakage current in like the one given direction. It's just there might be just a little bit of, so it's like a quantum tunneling effect of an electron being able to go through the barrier of the p-doped region. But if there is leakage, it's a very, very tiny leakage, even less than diodes. It's properly tiny. So let's go ahead and discuss the PMOS transistor now, okay? So this is what was asked about earlier. What if we swapped the N and P regions? Okay? What would happen if we do that? So for the NMOS, which is what we were discussing until now, if the gate voltage is low, not much current flows, okay? But if the gate voltage is high, then VDS can send through some more current, okay? For a PMOS, the opposite is true. If the gate voltage is low, now the stuff can flow through. Think about this as the exact opposite of the original situation. So notice in this diagram, the p-doped regions are at the corners and the n-doped is at the center, okay? We apply a positive voltage to the top and we attract the negative charges here as we did before. But that doesn't do anything. We don't form a channel here because what we want to flow are positive charges, okay? Not negatives, because that's what we have a ton of in these p-doped regions. So just forming a channel of negative charges up here doesn't do anything. That's useless for us, okay? But if we apply a negative voltage or just a very low voltage, okay, I say negative, but in practice it's just a low voltage, then we do the opposite. We attract the positive charges to the top. This is a PMOS. We attract the positive charges to the top, and now we form a channel for the movement of those positive charges. And now, since the positive charges are what's flowing, if the drain is on this side and the source is on this side, current actually does flow in this direction now. It does flow from source to drain. So the current flow is opposite from the NMOS. The conditions at which current flows is opposite for the NMOS. It is literally everything is the opposite from the NMOS, but the physics is the same, okay? The PMOS is still regulated by the gate, but the key difference is that low voltages open the gates instead of high voltages. Do they have the same purpose? So the purpose is actually that we use them together for complementary MOS circuits, which we'll see soon. So I guess you can say they have the same purpose. They're both transistors, but I mean, if you're building a circuit with transitions, you choose them based on what you need. To do this, you must have flipped the battery. Yeah, yes, you're right. Okay, so now we're gonna simplify things. I know it seems really complicated right now, but actually we're gonna get a little simpler here. Okay, so if you're lost, as Philip Phillips once said, you can always be found, just though you're not alone. I don't remember the rest of that song. Okay, let's compare the behavior of an NMOS transistor and a PMOS transistor. Okay, if I apply a large gate voltage to the NMOS, do I allow or do I prevent current? Someone answer me just quickly. If I apply a large gate voltage, am I allowing or preventing current? Allow, exactly. We're opening the gate. Okay. If I apply a large gate voltage to a PMOS, am I allowing or preventing current? I showed it, but do we understand why this is true? I flashed the answer, but do we all understand why this is true? Does anyone not understand why this is true? So if we have a device that allows a very tiny bit of current for a very large voltage, what do we call that device? Well, to me, that just sounds like a very large resistor, right? A very large resistor takes a very large voltage and allows only a tiny bit of current, right? V equals IR. If V is very large and I is very tiny, that means R has to be very, very large. And in the same way, something that allows a lot of current for a given voltage is like a small resistor, okay? And so if when the gate voltage is high, we're allowing a lot of current for a given VDS, we can just model that as a small resistor. And for a PMOS, if the gate voltage is high, the gate is basically closed, we're allowing only a tiny bit of current, we can just model that as a really big resistor. And we can do the same thing as the converse, okay? So now this diagram's a little complicated to look at, okay? Let's go one at a time. If the gate voltage, first focus on this one, okay? If the gate voltage is high for an NMOS, the gate is open and we're allowing lots of current, okay? That means we're like a small resistor, 25 ohms. If the gate voltage is low for a PMOS, that means the gate is open. We're allowing lots of current. It's like a small resistor, okay? Again, if the gate voltage is high for if the gate voltage is low for an NMOS, that means we're not allowing much current because the gate is closed, which means we're like a very big resistor. And if the gate voltage is high for a PMOS, the gate is closed and we're not allowing much current, like a big resistor, okay? Does this logic make sense to everyone? This is the most important part of this lecture. So if you're not clear on this, please say so. Does everyone understand? Yeah, I'll re-explain it. Okay. So, stop it. Okay. So, when we apply a large gate voltage to the NMOS, are we allowing a prevented current? We're allowing current, right? It's exactly like opening that faucet. If we apply a large gate voltage to a PMOS, we're preventing current, okay? And a device that allows a small amount of current for a big voltage is just a big resistor. And similarly, a device that allows a lot of current for a lot of voltage is like a small resistor, okay? So instead of thinking about it with these really complicated equations that I showed on this slide, we're just going to think of it in only two scenarios, big voltage and small voltage, okay? So for big high voltage at the gate for an NMOS, that means the NMOS gate is open, current can flow, small resistor. For a PMOS, high gate voltage means it's closed because the PMOS is the opposite of an NMOS. So high gate voltage means it's closed, not much current, very big resistance, okay? And we can do the same thing with the other scenarios. Low gate voltage for NMOS means the gate is closed, so it's like a big resistance. Low gate voltage for a PMOS means the gate is open because it's the opposite of an NMOS, which means we have low resistance, okay? So for our purposes, there's no in between. We're only considering the transistor is on or the transistor is off, okay? And whether it's on or off is regulated solely by the gate voltage, okay? That's all that regulates the on or off, okay? So yeah, Jay just sent that. Just commit that to memory, okay? It's a very logical thing to think, but that's just like, it has to be second nature to think that, okay? What are some ways to remember which is which? So first of all, you should think about just like the fundamental physics of how the device operates, right? So for an NMOS, to open this channel, I apply a positive voltage to pull up negative charges because negative charges flow. If you don't want to think about the physics and you want an easy way out, then what I would recommend is thinking a PMOS. I don't have a good shortcut for remembering it. Like even now,
it's like N needs high voltage, and then you can just know the other one's the opposite.
Well, you could say N needs low voltage and remember it the same way. Just remember the wrong thing.
Oh yeah, that's actually true. Yeah, there's no good way to remember it.
The best way to remember it is to really force yourself to understand the fundamental physics, because it's not a hard thing to kind of just mentally derive on the spot.
Yeah,
it's okay.
If you don't fully understand the physics, then we highly recommend just memorizing it, because we do understand that this is pretty difficult material. So,
okay, let me just reiterate it one more time. On means small resistance, okay, and off means big resistance, okay. And we're just gonna take transistors and circuits and replace them with on or off resistors, depending on if we know what their gate voltage is, whether it's high or low. We're just going to assume that the gate voltage will always be high or low. There's going to be no in between. Okay? This is the digital realm, logic, binary 1 and 0, high or low. So remember, an NMOS transistor is on when VG is large. Okay? A PMOS transistor is on when VG is small. Okay? So now let's connect them like this. Let's make a circuit with these transistors. We have a P-channel transistor connected to an N-channel transistor. In other words, a PMOS connected to an NMOS. And notice they have the same gate voltage, okay? We're using the same input voltage at their gates, okay? So let's first consider the situation in which Vin is large. So if Vin is large, someone tell me, is the PMOS on or is the PMOS off? Vin is large. Is PMOS on or is PMOS off? It's off, right? Because we're giving a very high gate voltage. And high gate voltage for PMOS means off. And what about the NMOS? Is the NMOS on or off? On, exactly. So we replace this with this circuit right here. Okay? Now notice, this circuit we know how to analyze. It's just you have voltage, you have resistance, you have current. So what is this voltage approximately right here? Is that voltage very close to 0 or is that voltage very close to 3.3? Someone tell me. It's very close to 0. The majority of the voltage is going to be dropped by this guy, right? And so this V out is going to be basically equal to 0 volts. So we took a high V in and turned that into a low V out. Okay, now let's do it the other way. If V in is small, then the gate voltage at the PMOS is small. So is the PMOS on or is the PMOS off? PMOS is on. And is the NMOS on or is the NMOS off? It's off, exactly. So we replace it with this guy. And now, is V out high or is V out low? Is V out going to be close to 3.3 or is V out going to be close to 0? Exactly, it's high. So what we've done is we've made a thing that turns a high V in into a low V out and a low V in into a high V out. We call this the CMOS inverter, complementary. That's what the C stands for because it has a P and an N. They're complementary to each other. MOS because they use metal oxide semiconductor devices. And inverter because it inverts the V in. This is the building block. I cannot stress enough, this is the most important transistor circuit that you can write down. If you remember when we were looking at the circuits, let me just pull it up actually. When we were looking at the circuits from last time, the primary issue we had was that these diodes, they can't take a high input and output a low, right? If I send a high voltage in here, a very positive voltage here, I'm going to get that positive voltage out right here. We have no way of inverting the input to a diode. But now what we've made is a device that can input things. This is a NOT gate. This entire thing right here, we draw in digital logic as a NOT gate. Okay, and we'll talk about this next time, but that's what a NOT gate is. And all other pieces of digital logic, so you might have heard this before that the NOT gate is a universal piece of digital logic. All other pieces of digital circuitry can be made from a NOT gate. So there's a summary. I think we're running out of time though. So the attendance code, how did you know that? Oh, but it's Jay that said that. Okay. Yeah, the attendance code is WhatsApp. But yeah, so we're gonna talk more about the inverter starting next time and get really into the nuts and bolts of digital logic. Okay. So was that so bad? I think most of us understand what's going on. If you don't understand, rewatch the lecture or look at the slides. Veritasium, to my dismay, actually has a pretty good video on transistors. I don't really like Veritasium's channel much, hot take, but his transistors video is quite good. I can't lie.
His older videos are really nice. I think I really enjoyed back when
His recent videos are like sensational physics. It's kind of I don't like it as much.
Let's see. We do have a couple minutes. So if you are a bit confused, then I just want you guys to remember that our transistors are really just acting like switches, and our gate voltage is what turns them on and off. If you can get that from that lesson, you should be pretty good for tomorrow. Or sorry, Wednesday. And
Sensational
remember, there
physics.
will be at 9 p.m. Eastern, there will be a lesson on, was it Devian Norton and sensational physics. You can get into that.
Sensational physics is just like, oh, black holes, quantum entanglement. It's just like buzzword physics.
Mm-hmm. Yeah.
As a physics major,
like
I think
quantum stuff. Usually, the quantum stuff is pretty bad.
Quite.
So
the problem is a lot of physics majors don't even like evolve past that. I should stop recording.